Hello, this video is going to involve something called the chain rule. The chain rule is a rule for taking derivatives that involves doing things in steps, the first part and a second part, kind of lined up in a chain. We use it when we have composite functions. So here is an example of what we could call a composition of functions. If I have h of x is the square root of 3x plus 1. This is a composition. Because what we're actually doing is we're taking two simpler functions, the square root function that we would usually just write as the square root of x, and then the function 3x plus 1, which is just a line and pretty easy. And we're doing them back to back. We're starting with x, we get 3x plus 1, and we take the square root of that. So we're applying this function to that function. We're not literally taking the square root of x. We're taking the square root of something else. So it's a function applied to a function. That's called a composition or a composite function. And we are comfortable with these functions individually from a calculus point of view. I know that if y is equal to the square root of x, that's x to the 1/2 power. So the derivative is 1/2 times x to the negative 1/2. And I know if y equals 3x plus 1, then y prime is equal to 3. So our hope is if we're comfortable with these individual functions, we should be able to figure out what the derivative is when we combine them. And this happens in the chain rule. So I'm just going to give you a heads up. This looks super duper abstract, and it is. I'm going to formally cover these rules, but we're going to get good at this by wrapping our heads around the idea rather than formally following these formulas. So here's one way of saying it. Let's imagine that we have a function where y is f of u. So essentially, I apply the function f to u to get y. And then we also have that u is g of x. So what's happening is we get from x to y through this intermediate stage. I apply g to get something, and then I apply f to get something. What the chain rule says is when we put that whole process together, y is f of g of x, that is a differentiable function, assuming the original functions were differentiable. And the rule for the derivatives is that the overall derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. It kind of feels like these things just cancel. That's one way of looking at this. The other is that when we have this composition function here, its derivative is f prime, right? F here is the function that comes first in this, writing it left to right, although it's actually the one we do last. So it's f prime of g of x, the thing that was inside the parentheses, times g prime of x. So again, all of this is very abstract, right? Nobody actually, well, I take that back, but hardly anyone does the chain rule by mechanically plugging into these formulas. We're going to develop some intuition about this that you'll get from doing problem after problem after problem. You really want to practice this. If you practice this, you'll have a good sense of just how this works. If you're just writing down this formula on a note card and hoping you can do it for the first time on a quiz, it's going to be really, really hard. So really try to think along with these examples and do as much as you can for practice. Don't just copy what other people are doing. Wrap your heads around how this works. And I just want to warn you that we use the chain rule only when we have a composition of functions, one function applied to another. Right here we are applying square root to the function 3x plus 1. This is an example where we would do the chain rule. But if we just had square root of x times 3x plus 1, here we're just applying square root to plain old x. We're not applying it to any more exotic function. So this would be an example where we did product rule. Only when it's a function of a function. So I'm going to help you out with this strategy and then just example, 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 example. So this is what our formula looked like, the second formula. Here is what you want to get good at. You want to look at composite functions and get a sense of what is your outer function and what is your inner function. So f here is our outer function, and g is our inner function. Sometimes we can tell outer or inner just by looking at parentheses, but you also want to appreciate which one do I actually do first. If I gave you this expression, we'll notice, so if I had, say, f of g of x, and suppose I wanted to do f of g of 2, what would I actually compute first? I would compute g of 2 first. If I was trying to get an answer, I'd think about what does g do first. So that's the inner function. It's the one we have to figure out before we can finish. And then once I have that, I apply f, which is the outer function. Get in the habit of identifying inner and outer. And the way this works is the chain rule says this derivative of the composite function is going to be two derivatives multiplied together. It's going to be the derivative of the outer function times the derivative of the inner function. I'm going to write this down. Well, I have it here, right? The overall derivative is the outer derivative times the inner derivative. And more specifically, it's the outer derivative applied to the inner function times the inner derivative. To emphasize that applied to the inner function part, you're going to hear me talking about just having a function of something. I don't want to get too caught up on what's inside. I just want to focus on that pattern. I'm taking the outer function of something. Very abstract, very hard to think about. Let's do some concrete examples. So here's the one that motivated us. Let's differentiate this function. H of x is the square root of 3x plus 1. So the first thing I want you to do, I want you to look at this expression and try to identify what operation are we doing on the inside, right? Basically doing first if we had to plug in a number. And then what are we doing afterwards? What are we doing last to get our final answer? So my hope is that you're realizing that the inner function is 3x plus 1. Right? We don't really need to give that a name. We have its formula. On the inside here, I am doing 3x plus 1. Then once I have 3x plus 1, I'm applying the square root function. And I'm just saying square root. I'm not really worrying about how I write that down. I want to think about this just in terms of input. I think I mentioned this here. Yeah. So for the outer function, I'm going to verbally describe it, and I'm just going to talk about what it does to its input. On the outside, I am taking the square root of something. Not literally the square root of x, just the square root of something. And I'm going to totally cheat and actually write it like that. I really just want to emphasize what that outer step is. The outer step is taking the square root of something that I already have. So now let's think about the derivatives. Right? At some point, you'll be able to do all of this just by thinking about it. I'm trying to make sense of some scratch work. I need to move my room because, actually, never mind. There may be an awkward pause here. I don't want to break this into two videos, but if I stop for a few minutes, just bear with me. It's because I'm moving rooms. So now let's think about these outer and inner derivatives. If my inner function is 3x plus 1, then my inner derivative, the derivative of 3x plus 1 is just the number 3. And for my outer function, I'm going to just repeat this. My outer function, I'll write it with a y. I have y is the square root of something. That is something to the 1/2 power. So my outer derivative, and this is just scratch work on the side because it's not real mathematical notation. I would think the derivative of something to the 1/2 power is 1/2 of something to the negative 1/2. I'm avoiding using the variable name x or any specifics. I'm really just focusing on this pattern. Right? If my variable was called x and I'm doing this with x to the 1/2, this is the pattern for the derivative. If my variable was called t and I was doing it with t to the 1/2, this is my pattern for the derivative. Regardless of what we're calling that input variable, this would be the pattern for the derivative. And we'll remember that that something was actually just the inner function. But I don't want to dwell on that. Only when we get here. So I have this composite function. By the chain rule, the overall derivative of this thing is going to be the outer derivative times the inner derivative. My outer derivative was 1/2 times something to the negative 1/2 power. I'm just going to leave that blank for a little bit. My inner derivative is the number 3. And the something was just whatever was inside all along. My outer function was actually the square root of 3x plus 1. So when I look over here, that something on the inside, I'm just going to leave it as 3x plus 1. I was taking the square root of this thing, 3x plus 1, and I'm just going to leave it here in the first step. We'll think about its derivative in the second part, but if my outer function is just taking the square root of something, then my outer derivative is 1/2 times that thing to the negative 1/2 power. If we wanted to, we could simplify this answer. It's 1/2 times 1 over the square root of 3x plus 1 times 3, and maybe you could write it like this. In this section, I'm much more concerned with how do we apply this rule than how do we simplify particular answers. We're just going to do a bunch more examples. Okay, this one. I want you to look at p of x and try to identify what would you call the inner function here. What would you call the outer function? Pause and really give this some thought. All right, so when there are parentheses, usually we can get away with just saying the thing inside the parentheses is the inner function. So the inner function, you'll notice I'm not worrying about specific names like f and g and u and all of that, because the names are going to vary from problem to problem. I really want to focus on just inner and outer. My inner function is 3x minus 2x squared. And my outer function, I'm taking that thing and cubing it. So it's something cubed. Pause to understand the structure before you take any derivatives. So now by the chain rule, it's going to be outer derivative times inner derivative. My outer function is something to the third power. The derivative of something to the third power is 3 times something to the second power. What was that something that I was raising to the third power? It was the inner function 3x minus 2x squared. So that's my outer derivative. I was taking something to the third power, so my outer derivative is 3 times something to the second power. It's like I'm treating this as though it was just x. Then for my inner derivative, I'm looking at this inner function and taking its derivative, and that would be 3 minus 4x. And I have just made a mistake that people make a lot. Technically, this answer is wrong. It needs to be entire outer derivative times entire inner derivative. So make sure that both of them are in grouping symbols if you need them. Here we absolutely need these. Otherwise, only the 3 is multiplying the first part. Here, if you wanted to put in grouping symbols just to be safe, there's no problem with that. The first set is not necessary, but go for it. And this is pretty much as simplified as it can get. We can rearrange things. So I might just put the most complicated thing last, but that's really not necessary. Let's look at another example. Now this one might feel like a quotient rule problem. Here's what we want to do. We want to look at fractions sometimes. And if the numerator is just a number, before we do any calculus, let's try to break it up, right? We did this before. Let's try to separate the number part from the function part. So I'm going to think of this as 5 times 1 times 1 over 4x minus 3 squared. So what I actually have here is 5 times 4x minus 3 squared. Not squared, yikes, to the negative 2. So when we see a fraction, sometimes we can rearrange things and write it with a negative exponent and avoid the quotient rule. So when we take the derivative here, there's just this coefficient of 5 in the front. And then for the rest of it, we're going to use the chain rule. We'll use the chain rule on the part that actually has x in it. It's going to be outer derivative times inner derivative. So looking at this part over here, the parentheses are a really big help. Hopefully you're realizing that your outer function is something to the negative 2 power. And our inner function is 4x minus 3. I might switch it up how I identify those. Usually you're sort of recognizing them at the same time, inner and outer, outer and inner. So write them down in whatever order occurs to you. Although usually when we do the derivative, we'll write outer first. So my outer derivative would be the derivative of something to the negative 2 power. So that would be negative 2 times something to the negative 3 power. I'm just using the power rule. What is that something? That something is the 4x minus 3 that was inside. And then times my inner derivative, which is just the number 4. Outer function is something to the negative 2, so the derivative is negative 2 times the same thing to the negative 3. Inner derivative is just the number 4. So if we wanted to, we could write this as, let's see, 5 times negative 2 times 4 is negative 40. And then we have 4x minus 3 to the negative 3. If you wanted to get rid of the negative exponents, here's a way of writing your final answer. 2 more. Look at this one. What would be your outer function? What would be your inner function? My outer function is something squared, and my inner function is that whole fraction. Sometimes the inner function is not particularly simple. That whole thing is my inner function. So to take the derivative, we're going to use chain rule. It's going to be the outer derivative. Well, my outer function is something squared. The derivative of something squared is just 2 times that something, raised to the first power, which you don't really need to write. And that something is 3x minus 1 over x squared plus 3. Now I multiply by my inner derivative, which uses the quotient rule. So this is a chain rule problem, but it has a quotient rule step. We're using the chain rule to structure the whole thing, right? It is something squared. It is a function of a function. But one of the derivatives I need along the way maybe requires a different rule. So here I'm going to do quotient rule. I'm going to create my scaffolding before I fill in any details. derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And for this one, let's just leave it as is. Sometimes on quizzes and tests, I will encourage you to leave your answers unsimplified because I just want you to demonstrate your thought process. But you need to be careful that you have all your parentheses and fractions in the right place. So just double check that. Outer function is something squared, so 2 times that something. Inner function is a fraction, so I do quotient rule. All right, and then one more, this will have an application. So find an equation for the line tangent to this graph at the point 2, 4. So if you were to graph this, it's not literally a parabola, but it kind of reminds us of a parabola a little bit. And it goes through a point at 2, 4. I want to find an equation for this tangent line. Let's rewrite this. So we can actually write this as x squared plus 4 to a single power. I have a radical, I have squaring. Think about how you can combine those into a single power. So hopefully you understand that a cube root is like a 1/3 power, and squaring is like the second power. When we have both of those applied, this is actually the 2/3 power. You do need to be familiar with exotic powers like fractional powers and negative powers in order to apply the calculus rules. So ask yourself, what's the outer function? What's the inner function? We will do the chain rule. My outer function is something to the 2/3 power. So my outer derivative is 2/3 times that something to the negative 1/3 power, where that something is x squared plus 4. My inner function is x squared plus 4. The derivative of that is 2x. So that's my derivative by chain rule. And what am I doing in this problem? I'm trying to find an equation for the tangent line. I already know this point, but I also want to know what's the slope. So that's why I took a derivative in the first place. I want to know the slope of the tangent line. And specifically, I want to know the slope of the tangent line when x is equal to 2. So let's just plug that in. G prime of 2 would be 2/3 times 4 plus 4 to the negative 1/3 times 4. A negative 1/3 power means a cube root in the denominator, and 4 plus 4 is 8. So we have 2/3 times cube root of 8 is 2 times 4. And this all simplifies to 4/3. So here's what we know about that tangent line. We know that a point on that tangent line is 2, 4. We know that the slope of that tangent line is 4/3. So if I just want to do this in point slope form, y minus that given y coordinate is slope times quantity x minus our given x coordinate. If you want, you can do a little more math to get it in slope intercept form. And it would look like this, if I'm doing my arithmetic correctly. I'm a big fan of just point slope form. You need to just do a bunch of these so that you're thinking about them correctly. You'll notice for every single one, I'm just talking about inner and outer and something. I am not mechanically following that formula. I'm not asking, oh, what is F, what is U, what is G? I'm really just using this pattern of inner and outer. That's how you want to think about it. You want to get good at looking at a composite function and understanding, oh, this whole fraction is my inner function, squaring is my outer function. So to take the derivative, it's outer derivative times inner derivative. Focus on the pattern. Do not just think memorizing a formula will get you there. Okay, That's it.